Okay, we're looking now at section 5.8, and we're just going to go through the problems that are assigned in the homework along with the lecture notes. So it says, and I hope that you will print out a blank copy of this and fill in as you go along, trying to pay attention. It says, in this section we will explore some applications of the exponential function. We want to consider a quantity p of t that depends only on time. So the amount that you have left after a particular period, p of t, it depends on the p naught and then e to the kt. So since it depends only on time, p naught and k must be fixed values. And we say that p of t then grows exponentially. K is called the growth constant, and p naught is the initial amount or the initial size or the amount at time 0. Because obviously if you plug 0 in for t, that'll be e to the 0, which is just 1. So you'll get p naught, or your initial amount. Now, it could also be true that if you wanted, you could write it as p naught b to the t, where b is equal to e to the k, and then b to the t would be e to the k to the t, which is e to the kt. So that's kind of important for that first homework assignment, or for the first homework problem. But if you have a negative k, we say that it decreases exponentially, and it's a negative k. And when it's greater than, when k is positive, you have exponential growth. So you either have exponential growth or exponential decay, depending on the power of the positive or negativeness of your exponent. Okay, so let's look at this first question. It says, write f of t equals 5 times 7 to the t in the form of f of t equals p naught e to the kt for some p naught and k. So they just want you to kind of be familiar with this notation here. So if we wanted to, we could just take a look right back at this right here, thinking right now we have, this is p naught, and then this is b to the t. So it must be that b is equal to e to the k, so 7 is equal to e to the k. So if we want to figure out what k is, we can take the log of both sides. We get ln 7 is equal to k times ln e, because remember that invokes the power rule, which will bring that k out in front. And of course the ln of e is just 1, so we know that k is equal to ln 7. So if we want to write our equation then in this form, f of t equals p naught e to the kt, we can write it as f of t equals p naught, which is that 5 right here, and then e to the k, which is ln 7 times t. So all they really want you to do on number 3 is just kind of notice how you can write one in the form 5 times 7 to the t in the form of an exponential equation, where the k then is your ln 7. Okay, so the next question, or the next realization here, is that they want you to understand that the important role played by the exponential function is best understood in terms of the differential equation y prime is equal to k times y. And it turns out that the function y equals p naught e to the kt satisfies this differential equation. Remember, this is the if you find the antiderivative of this function right here, you will get, if this is what you will get, this function, meaning that if you take the derivative of this, you should get this y prime equals ky. So if you take, here's where they're going to take the derivative with respect to t of p naught e to the kt, and remember, p naught's just a constant. The derivative of e to the kt is just k times e to the kt, so there's your k, and then p naught e to the kt, well, that was what you had originally. So this is the only type of function where this happens. If y of t is a differentiable function satisfying the fact that y prime is equal to k times y, then you know that you have an exponential function, and p naught is your initial value, where which is the amount that you have at time 0. So this is just drawing your attention to this conceptual insight. Theorem 1 tells us that a process obeys an exponential law precisely when its rate of change is proportional to the amount present. So this comes up a lot in like your biology and chemistry classes. The rate of change is proportional to the original. Okay, so looking at number 5, it says a certain RNA molecule replicates every 3 minutes. So just take that sentence. So it replicates every 3 minutes. So say you had 5 of the molecule, then after 3 minutes you would have a replication of it. So you would have 10. If you had 4 of the molecule, then after 3 minutes you would have 8, because you have this replication that occurs after 3 minutes. Okay, so that's kind of this idea, this first idea that we need to think about. Then it says find the differential equation for the number n of t of molecules present at time t in minutes. And then it says how many molecules will be present after 1 hour if there is 1 molecule at t equals 0. Okay, so this information right here is your initial amount. That's P naught. P naught is equal to 1, because at time 0 you have 1 molecule present. So if we want to find if we're looking for our equation, here we know that n of t is equal to P naught e to the kt. P naught e to the kt, and we know that P naught is 1. So the first step we have is we can say that n of t is equal to e to the kt. But we need to figure out what k is. So we have to think about what other information did they give us that will help us determine what k is. All right, well, let's think about that for a second. It says that the molecule replicates every 3 minutes. So if you start with some amount, you don't know, say you start with, well, let's just say our initial amount was 1. How much will we have after 3 minutes? Well, we'll have a direct replication, so we'll have 2. So 2 is equal to e to the k times 3. So we knew after 1 minute we had at time 0 we started with just 1 molecule, and then we'll have 2 molecules after 3 minutes. Well, this is good because we can then solve for k here. We'll get take the ln of both sides. ln2 is equal to, this is k times 3 ln e, and then solve for k here, and you divide both sides by, remember ln e is just 1, so just divide both sides by 3, and you get k is equal to ln2 divided by 3. So our equation n of t is equal to the initial amount, which was 1, and then e to the k, which is ln2 over 3, and then times t. Okay, now if you're following along in the solution manual, they kind of clean this up a little bit, and this is a little bit uncomfortable perhaps, but you can think of this, remember when it's a power to a power you can multiply, so you can think of this as e ln2 times t over 3, and e to the ln2 is just 2. And so this, you can really think of this as 2 to the t over 3. If you wanted to simplify this as 2 to the t over 3. But you can also leave it this way, that's fine. It's just something to note. So if they want to know how many are present after 1 hour, then n of 60, because remember t is in minutes, will be equal to 2 to the 60 over 3, or 2 to the 20, which is, you can type that on your calculator, 2 to the 20 is about, let's see, 1,048,576. So this one was a little bit tricky, kind of figuring out the k. You had to understand this ratio, that if it's replicating every 3 minutes, if you start with 1, then after 3 minutes you'll have 2. And so using that information, you can find your k and then write your equation. Okay. So let's try number 7. It says find all solutions to the differential equation y prime equals negative 5y, which satisfies the initial condition that y naught is equal to 3.4. Well, this is actually pretty straightforward. If you just look back at the theorem, the number in front of the y is your k, and P naught is the value you get at y0. So here our k is negative 5, and 3.4 is going to be our y naught. So our solution to this differential equation is just going to be y of t is equal to 3.4 e to the negative 5 times t. Okay, and you can check it. If you take the derivative of this, you will get what? Y prime of t will be equal to 3.4 times the derivative of e to the negative 5t is just negative 5 e to the negative 5t, right? Well, that is just a number times your the 3.4. I mean, you can see right there, that's exactly what you have. 3.4 e to the negative 5t, that was your y of t, and then you have the negative 5, so it's negative 5 times y of t, which is, or just negative 5 times y, which is kind of this idea of this differential equation here. So it's kind of, seems kind of redundant, but it's just the nature of the exponential function there, that when you take its derivative, it's just proportional to the original. Okay, so number 8 is going to be very similar. This is your k, square root of 2, and then 20 is your p naught. So you're going to have y of t, your original function, is just going to be p naught e to the kt, which in this case, p naught is 20, and then it's e to the k, which is the square root of 2, and then t. And so you should see that's pretty straightforward. If you take the derivative of that, you will get e to the square root of 2t times 20 square root of 2, which is what you started with there. So it's just kind of helping you see how to plug these in. Okay, now it turns out that you have these ideas of half-life and doubling time. If you have exponential decay, then you have a negative exponent, and the half-life is the time that it takes for the quantity to decrease by a factor of 1/2. And I copied these out of the book out of order, and so they say it's similar to that of doubling time, but let me imagine, say we have this function p of t is equal to p naught e to the negative kt. Well, if you think about it, it doesn't even matter how much you start with. If you want to know how long it will take for you to end up with half of what you started with, well, then you could just replace p of t with half of what you started with, no matter what you started with is, just like that. And then you'll still have the p naught e to the negative kt. And then your p naughts would cancel here. You take the ln of both sides. You'll have the ln of 1/2 equals negative kt times the ln of e. Well, the ln of e, of course, is just 1. And so you have the ln of 1/2 divided by negative k is equal to t, which would be how long it takes to end up with half of what you started with. Now, if you simplify this, if you use properties of logarithms to simplify this, this is going to be ln 1 minus the ln of 2 divided by negative k. But you might remember that the ln of 1 is 0. So this t then is just the ln of 2 divided by k. So that's where they come up with that formula for half-life. You just take the ln of 2 and divide by k, and that's going to be your half-life when you have exponential decay. But if you have exponential growth, if you're starting, you have your same equation, p of t equals p naught e to the kt, but now you want to know how long it takes for something to double. Well, it doesn't actually matter how much you initially started with. It's just that you want twice what you initially started with is what you end up with. Okay, and so you can solve this equation. Notice the p naughts cancel, and if you take the ln of both sides, you'll get the ln of 2 is equal to e to the kt, ln, and the kt comes in front, kt, ln e is 1, and so that's just going to be ln 2 divided by k. So when you have exponential growth, meaning your k is greater than 0, the doubling time is ln 2 divided by k. When you have exponential decay, so you have a negative in front of your rate of growth, it's a negative rate of growth, then your half-life is ln 2 divided by k. So these are just two formulas which you can memorize, or you can just derive them each time if you want. right, so here they tell you, number 12, it says the half-life of radium-226 is 1,622 years. Find its decay constant. All right, so you know that the half-life formula is equal to ln2 divided by k. So just use the information that they gave you. It's 1,622 years for it to decay. So that's what you'll put in for the half-life. And then you have ln2 and then k. And then you can just cross multiply and divide to solve this. And you get k is equal to ln2 divided by 1,622. That is the decay constant, which you can get, you can get a decimal approximation to if you want, or you can just leave it in that form if you want. Okay? Now, let's look at number 19. It says, assuming that population growth is approximately exponential, which of the following two sets of data most likely represent the population in millions of a city over a period of 5 years? Now, if you're going to have exponential growth, you may remember this from a pre-calculus class. Exponential, if you have exponential growth, you have to have the ratio between successive years has to be the same. So what you want to do is you want to look at the ratio 3.36 to 3.14, 3.60 to 3.36, 3.85 to 3.60, 4.11 to 3.85. Look at that ratio, and then also look at these ratios and see which one appears to be have the same rate. So let me just get a calculator. I can just use a small calculator. So if I do 3.36 divided by 3.14, I get 1.07. That's this ratio of 3.36 to 3.14. So 1.07. Now let me try the next one. If I do 3.6 divided by 3.36, I get also about 1.07. And then let's see, 3.85 divided by 3.60. Oh, pretty close to 1.07. So I'm feeling probably like this first set of data is going to be exponential because the ratio between, if you look at the ratio between successive years, it seems like each time you get about the same number, 1.07. Whereas, let's see at the second set of data, if I do 3.24 and divide by 3.14, I get 1.03. If I do 3.54 divided by 3.24, I get 1.09. So right away, that is not looking like it's going to be exponential. So set 1 appears to represent the population because it looks like we have a ratio. The ratio seems to be 1.07. Okay, and so then let me see. So what was our initial amount? Well, in 2000, the initial amount was 3.14. So if you want to write our exponential growth equation, P of t, our initial amount was 3.14, and then we write our growth rate, which is 1.07 to the t. That would be a exponential model for the growth that we have for set 1. Okay, let's try number 20. It says the atmospheric pressure, P of H, in kilopascals at a height h meters above the sea level satisfies the differential equation P prime equals negative Kp for some positive constant K. So if you're on the final and you see this information, immediately you're going to want to write P of t equals P naught e to the Kt. So you already have, if you have this differential equation, then you can write the original function this way. Now, it says barometric measurements show that P of 0 is equal to 1.0 or 101.3. So this right here is your P naught, because that's how much you have at time 0. So you're getting closer to filling out your formula. This is going to be 101.3 e to the kt. Now, we want to find the decay constant, but they give us some other information. They say P of 30,900 is equal to 1.013. And I guess in this case, instead of P of T, I guess I should have put P of H, because they're talking about a height above sea level. So I'll just put H's wherever the T's are, but that's all it's still this exponential rate. Okay, and so I can then say that if 1.013 is what I get when I have 30,900 as my H. So you just want to solve this for K, because you're looking for the decay constant. So you can divide, this is kind of strange, you'll divide this number, 101.3. So if you do that, let's see, 1.013 divided by 101.3. Interesting, you get 0.01 is equal to EK to 30,900. And you remember from pre-calculus, to solve this exponential equation, you'll just take the natural log of both sides. So this is going to be the ln of 0.01 is equal to, that invokes the power rule, K times 30,900 ln of E, which is just 1, of course. And then so you can just divide by 30,900 to figure out what K is. And, okay. And, if you want, you can type that into your calculator. Let me get a big calculator out here. If you do, so we'll do ln 0.01 divided by 30,900, and we get this negative 1.49 e to the negative 4, which means move your decimal to the left 4 places. So you can say this is like 3 zeros in front, right? Negative 0.000149. So your K is approximately negative 0.000149. And so then if you want to know the pressure at H equals 500, P of 500 will just be P naught, which was 101.3, E to the K, which we now know is negative 0.000149, and then times H, which is the 500. So we'll just pop that into our calculator. So 101.3, and then second E, negative 0.000149 times 500 to get our answer there of 94.03 or so. Kilopascals. Okay. All right, now one of the main, or a real popular thing that exponential growth, or in this case exponential decay, is used for is carbon dating, which is kind of to see how old fossils and artifacts are. And it relies on the fact that all living organisms contain carbon that enters the food chain through carbon dioxide absorbed by plants from the atmosphere. Carbon in the atmosphere is made up of non-radioactive C12 and a minute amount of radioactive C14 that decays into nitrogen. So the ratio of C14 to C12 is approximately 10 to the negative 12th. So the carbon in living organisms has the same ratio because this carbon originates in the atmosphere. But when the organism dies, its carbon is no longer replenished, and the C14 begins to decay exponentially, while the C12 remains unchanged. Therefore, the ratio of C14 to C12 in the organism will decrease exponentially. So by measuring this ratio, we can determine when the death occurred. So the decay rate for C14 is this 0.000121 years. And so you have a ratio of C14 to C12 after T years is the RATM, which they give you as 10 to the negative 12 on the Earth, and then E to the negative, all of that. So that's our ratio. That's our formula for carbon dating that we have here. Okay, so it says a sample of sheepskin parchment discovered by archaeologists had a C14 to C12 ratio equal to 40% of that found in the atmosphere. Approximately how old is the parchment paper? So you kind of have to just use your little thinking skill, but you end up with 40% of what you started with. Now, what you have in the atmosphere is 10 to the negative 12. So now you have 40% of 10 to the negative 12 is equal to the 10 to the negative 12 and then e to the negative 0.000121 t. So just filling in this formula using 10 to the negative 12 as your ratio in the atmosphere, and that you have 40% of it. So that's what you end up with. So if you're clever here, you realize you don't even have to worry about this 10 to the negative 12 didn't matter. And you can solve this for t by taking the natural log. The ln of 0.40 is just going to be negative 0.000121 t ln e. And the ln e, of course, is just 1. So ln 0.40 divided by negative 0.000121 is going to be equal to the amount, or to the about how old it is. So if you do ln 0.40 and divide that by negative 0.000121, you get that it's approximately 7,572 years, maybe 73, 7,572.65. So that's just kind of an interesting application, really, of this. They round it to the nearest hundreds of years, so they say 7,600 years old, approximately. Okay, now number 25, this is the last one. It says a paleontologist discovers remains of an animal that appear to have died at the onset of the Holocene Ice Age, between 10,000 and 12,000 years ago. What range of the C14 to C12 ratio would the scientists expect to find the animal in the animal moraine? Well, that's not so bad because we have this formula that they gave us. The ratio is after T years is RATM e to the negative 0.000121 t, right? Well, and we know that RATM is 10 to the negative 12 on the Earth. So this is what we can expect, how much we can expect the ratio, how much we can expect there to be. So that's R of t at a given time. So all you have to do is just calculate R of 10,000, which you'll just type into your calculator, times 10,000. And then that would be at one value, and then also R of 12,000, because it's between 10,000 and 12,000 years. So you'll just plug these numbers in. Okay, so we could type these numbers into your calculator. Be kind of careful how you type them in. You're going to want to do 10 to the negative 12, and then times second e to the negative 0.000121 times 10,000. That's that ratio, 2.98 times 10 to the negative 13. And then if you put the 12,000 in, we can just do second enter and change that to a 12,000 instead of 10,000. And we get 2.34 times 10 to the negative 13. So those are kind of, those numbers don't really make a lot of sense, I guess, unless we're paleontologists, but that's the ratio that we would expect if we were looking at 10,000 years or 12,000 years. That would be if it was a 10,000-year-old remains or 12,000-year-old remains. Those are the carbon 14 to carbon 12 ratio that we would expect to find. Okay? All right, and that's it for this lesson.